the design verification stage. So, what we do, we verify whether the system has been designed properly or not. So, how do we verify? So, there can be two approaches for that. One is by means of some formal verification tool that will be proper verifying some properties on the designed system, and another easier technique for doing it is via simulation. So, simulation, so this will be applying some stimulus to the description, and it will see whether the result that is produced is as per the desired one. So, simulation tools are available, and simulation is much easier to do because for formal verification. So, we need some formal logical background, so that all the designers may not be having, but the simulation is more or less now the standard technique for doing this thing. So, design errors in behavior or the register transfer level description, so they can be found out by this simulation. So, at this behavioral level and the register transfer level, so they are actually with simulators are run, and the same stimulus is fed to both the stages, and as a result we can get the response from them and check whether the responses do match between the two stages. So, that if the responses match, that means this translation from behavior to register transfer level, that has been done correctly. If it is not, then there is some problem in this translation process, so that has to be rectified. So, that way these design errors can be detected. Similarly, after this register transfer level, so we have got this gate level description, where this the total RTL description is flattened into gates, and we have got a gate level netlist for the system. So, for this gate level netlist, so we can again run the simulator and see whether the system behavior is matching or not. And finally, at the physical level, the transistors, so there are some transistor level simulators like SPICE, so that can be run at the lowest level, and then we can see whether it meets the requirement of the system or not. So, that way at every level the simulators are used widely for getting confidence about correctness of the system. But still, up to this much we have got only description. So, it is at the physical level also, this is nothing but a transistor level description of the system. This is not the actual chip that is manufactured. So, as a result, when we go to the manufacturing stage, at that point after each level of manufacturing, we need to test whether the manufacturing process is correct or not. So, these simulators, they can catch the design errors, and these testing processes, they can catch manufacturing errors. So, we have got some parameters like yield. So, it is defined as the number of acceptable parts to the total number of parts that are fabricated. So, this ratio is called yield. Naturally, we will expect as a manufacturing process, in the manufacturing process, that yield should be maximized. Now, so the number of chips that we discard, that we had to discard as faulty, they should be minimum. Now, there are two types of yield loss that can happen: catastrophic. Catastrophic, they are due to some random defect. So, it may be some defect in the wafer at some point, so that cannot be avoided. So, that is one type of problem, and the parametric problem, because some parts may not be fabricated properly. As a result, there is the gate of a transistor might not be of exact length that we were looking for. So, as a result, it leads to some problem. So, these are known as parametric variations. So, they are the process variations, and they come under this parametric yield loss. So, the undesirable result during testing. So, these are the problems, like if my testing process is not proper, then these things can happen. A faulty chip may appear to be good. So, if it happens, then a faulty part, so that will be shipped as a good chip, and when this chip will be put into field operation, at that point of time at system level it will give problem. So, at a system level we have to take care, and by the rule of tens we know that by that time the cost of this mistesting will be very high, because that will be that may cause rejection of the full system. So, this is the reject rate. So, this number of faulty parts passing final test, that is they are declared as falsely as correct, and the total number of parts passing the final test. So, it is the number of faulty parts that are passing, the ratio of faulty parts that are passed, that has passed the final test. So, that is the reject rate. And another problem that can occur is some good chip, that may appear to be faulty. So, chip is actually good, but they fail the test. It can happen due to various reasons. A major problem is with power and temperature issues, like say maybe that it consumes a good amount of power, as a result the temperature also goes up and the delay variations occur. So, and also some points in the circuit, so it may not be very easy to test, and we may try to test it and we may fail. So, as a result that may also be taken as some good chip appearing to be faulty. So, this is also an undesirable thing. So, that should not happen. So, this can happen due to poorly designed tests, maybe the test patterns that we apply. So, they are not sufficient to they have the problem with the good responses for some faults. Even if that fault is not present, so it sometimes may be creating difficulty, and lack of this design for testability mechanism. So, that may also cause some good chip to appear as faulty. So, these are the two things that we would like to avoid. Now, in the system manufacturing process, a system consists of PCBs, that consists of PCB will again contain this boards. So, that boards will be they are actually the boards. On that board we will have the VLSI devices or the chips. So, PCB fabrication is similar to VLSI fabrication, because in the VLSI fabrication we are putting several layers of polysilicon and diffusion and all that. So, here also we are doing same thing, at different parts we are putting the chips and then we are making copper connections between them. So, they are also susceptible to defects, like two lines running parallelly on the PCB. So, there may be crosstalk, so there may be interference between them. So, as a result it may create problems. So, at some point of time that copper line that we are drawing, so there may be some break, etc. So, this is necessary. Similarly, assembly process, so that also susceptible to defects. So, testing process has to be there in all these stages. So, PCB fabrication level, PCB assembly level, unit level assembly and system level assembly. At all these stages we have to do this testing. So, at PCB level board test, PCB assembly level also we have got board test. Now, then at unit level unit test and system level system test. So, if we can detect a fault early, then we can avoid the losses. So, at a system level, so faults will occur during system operation. So, if say this is the if we plot the the lifetime of a system. So, over the lifetime, maybe from 0 to time t1, from t0 to t1 there was no problem with the system. So, that is normal operation. Then at time t1 some problem occurred and it required some time t1 to t2 for its recovery. So, recovery may be from various angles. So, it may be some transient fault, or it may be that there is some fault mitigation technique incorporated into the system. So, that takes care. Again from T2 it starts operating, or maybe the maintenance person so takes some measure by which this is corrected, the system is corrected, and then from T2 to T3 again it works normally, then at time T3 it failed. So, this is the, so these times T1 to T2, then T3 to T4, so these are the failure time. So, at these times the system is not available. So, there is an exponential failure law. So, it says the interval of normal system operation is random number exponentially distributed. So, if we want to find the probability that the system will operate normally till time t, then we have got this probability expression that up to till time t it will this time of failure is more than t. So, this is given by e to the power minus lambda t by this exponential failure law. So, the failure rate, so since my system may consist of a number of chips, so for the total system, so I can say the failure rate is the sum of individual failure rates. So, total lambda is given by sum of these lambda i's. So, if I have got k number of components, so this is sum of these k components. Then there is mean time between failure and MTBF. So, to find it, so we can say that this repair time is also assumed to be, it will follow this now exponential distribution. So MTBF is given by this expression. So it is an integration of that failure time e to the power minus lambda t dt. So if you integrate over 0 to infinite time, so this is 1 by lambda. So this mean time between failure is 1 by lambda, and repair time. So this is also assumed to be exponentially distributed, and if mu is the repair rate, then the mean time between mean time to repair MTTR is 1 upon mu. So system availability, that is how much time the system is available. So this is basically the mean time between failure divided by the total time for the system. So this MTBF divided by MTBF plus MTTR. So this is the fraction of time system is operating normally. So that is system availability. Okay. So high reliability systems, so they should have this availability is more than 0.9999. So it is a very high requirement that we have, that a system must be available almost 99.99% times. So this is referred to as law of 4 nines, because 0.9999, that is why. So at a system level testing, so testing is required to ensure that the system is available. Now there are types of system level testing like online testing and offline testing. So online testing is when we are doing the system is operating, and simultaneously we are doing the testing. So we capture some data from the system operation and try to analyze and see whether the system is working correctly or not. So that is the online system. And offline testing, so this is here also the system is operating, but we stop the operation temporarily for some time, and then we do the testing at that time. So when the system is not doing some high demand job, it is doing some low demand work, then we can suspend that low demand work for some time, and we can use this we can do this testing for that. So this can be used for diagnosis. Okay. So of the faulty replaceable components that we can replace, and that can improve the repair time. So the system level testing is done both online and offline. So there are test techniques for both of them. Then comes the problem of test generation. So what is a test? A test is defined to be a sequence of test patterns, that is a set of patterns that they are also known as test vectors that are applied to the circuit under test, and we apply the pattern set, and then we see what is the output. So for a set of input patterns there will be a set of outputs. Now this set of outputs, so they will be checked with the correct responses. So if we find that the responses are correct, they are same as the correct response or golden response, we say that the circuit under test is functioning properly. So this is tested okay. Now there can be many approaches by which we can do this testing. One possible approach is exhaustive testing. So we apply all possible test patterns to the circuit. For if a circuit has got say 10 inputs, and assuming that all these 10 are they are binary input, then we have got all possible patterns. So 2 to the power 10 different possible patterns that can come as input to this system. So for all these 2 power 10 patterns, so we check whether the output produced is as desired or not. So that is known as exhaustive testing. So all possible test patterns are applied to the circuit and the responses are checked. Naturally, the cost of such a testing is very high. Like for 10 input, I can apply 2 power 10 patterns. So if I have got 100 inputs, I have to apply 2 power 100 patterns. The 1000 input, 2 power 1000 patterns. So that takes the test cost to be enormously high. So you cannot go for that. So exhaustive testing is normally done for small systems and which are very critical. So maybe number of inputs are less, but the operation is very critical. So we can go for exhaustive testing. Functional testing, so testing every truth table entry for a combinational logic card. So we can go for say, at the truth table entry, so where it says that it is a 1, so we apply those patterns only and see whether it gives work or not. Similarly, when the truth table says it is 0, so we see whether it is giving a 0 or not. So they are not practical. So both this exhaustive testing, functional testing, so they are not practical. So what is happening in functional testing? we are looking at a functional level. So it may be it may not be true at a gate level operation. So for the entire combinational logic, so we are testing that way. But for exhaustive testing, so we may be testing each and every gate in the circuit exhaustively. So that way there is a difference, but in both the techniques, so they are going to take exponential amount of time. So fault coverage. So what is the way out? So way out is to apply only a subset of test patterns, not all these exhaustive patterns. So if we apply a subset of test patterns, naturally we cannot expect that all the possible faults in the circuit, so they will get tested, only a part of it will get tested. So that gives us a measure called fault coverage. So that is how many of the faults can be detected by the set of applied test vectors. So if we want that this fault coverage should be as close as 100%, but it is very difficult to achieve. Next we look into the test generation process. So fault coverage, as I was telling, so it is defined as the number of detected faults divided by the total number of faults. So for a given test vector set, so this is the measure of fault coverage. So 100% fault coverage may be impossible due to some undetectable fault. So we will see what is an undetectable fault. Essentially what it means is that due to some redundancy in the circuit, so some faults can never be excited by applying some patterns. So as a result, so we cannot test those faults. So that way there is we cannot get 100% fault coverage, but even the circuit does not have redundancy. So in those cases also it is very difficult to get 100% fault coverage, because it will require a very large test set. Okay, so test vector set will be very large. So that is why 100% is not achieved in most of the cases. So fault detection efficiency, so this is defined to be the number of detected faults to the total number of faults minus number of undetectable faults. So this is basically, this denominator gives us the total number of faults that can be detected, and this numerator is the number of faults detected by a particular test set. So this ratio gives us the fault detection efficiency of a test set. Then there is something called a reject rate. It is 1 minus yield to the power 1 minus fault coverage. So this measure is known as the reject rate. So for an example, if a PCB has got say 40 chips, each with 90% fault coverage and 90% yield. So if you 90% fault coverage, so it is 0.9. So the reject rate will be given by, for a particular chip will be 1 minus yield. So yield is taken as 0.9, 1 minus 0.9 to the power 1 minus fault coverage, that is 0.1. So this whole thing, I have got 40 such chips. So if you calculate, so it will turn out to be so per million. So per million, so so many chips, so 4,19,000 chips will become faulty. So that's a huge number. So you see, we even with say 90% fault coverage, we have got a very large number of defective parts that are produced, and that will get rejected after they have been shipped. So it is necessary that our fault coverage is even higher than 90%. So that gives the challenge that we have. So a value of fault coverage say less than 95-96%, so that is not going to be acceptable. So what is this test generation process? Like, the goal of the test generation process is to find efficient set of test vectors with maximum fault coverage. So that is the overall goal. So there are several techniques by which we can generate test vectors. So we will see those in due course of time. Now how do we say that with how many faults this particular test set can detect? So for that purpose, the certain techniques have been developed which are known as fault simulation. So fault simulation, it will try to see, like, for a given set of patterns, what are the faults that this set of patterns can detect. So that is the fault coverage. What is the fault coverage? So naturally it will require the fault models to emulate the behavior of defects. As I was telling, the physical defects are emulated by means of faults. So these fault models will be used. So, we will see that what type of different fault models can be there, but a good fault model, it should be computationally efficient for simulation. So, it should not be very difficult to compute the value of a the values of different points in the circuit due to application of a test pattern under that particular fault model. So, that is the one requirement, and second requirement is that it should accurately reflect behavior of defects. So, the difference between the actual defect behavior and the actual fault behavior, they should not be much different, they should be as close as possible. The difficulty is that no single fault model works for all possible defects. So, this is another catch. So, as a result, we will see that different fault models are to be used, and when we are doing the test generation, so we have to assume the assume this generation process on some fault model. So, that fault one particular test generation process will not be able to cater to all possible fault models, because that is not possible. So, they will be so that way we will have different fault test set generation process. To give you some idea about these fault models, a given fault model may have k different types of faults. Okay. So, k equal to 2 for most faults, like say you can say that if there is a signal line running in this in the chip in the system, then the signal line, a possible fault is that this line is permanently 1 or permanently 0. So, as if there is the VCC line running and there is a short between this line and this. So, as a result, this line has to be treated as permanently 1. So, this physical defect is modeled as permanently 1. So, that is known as stuck at 1 fault. Similarly, if this line is shorted with, say, the ground line, so we have got this another fault which is permanently 0. So, when we are talking about, say, logic gates, the inputs and outputs, then this model is a very ideal one, because a logic gate has got some inputs and some outputs, and the fault that can occur is the line one of those lines becoming permanently 1 and permanently 0. So, that way every fault in this particular case, they have got two types of faults. Okay. Now, if a given circuit has got n possible fault sites, then so depending upon the number of lines that we have in the system, so there may be n number of lines, and each of these lines may have the fault. So, as a result, there are n possible faulty sites. Now, there can be multiple fault model, like circuit can have multiple faults, like in apart from single fault, maybe in so if out of these n sites, maybe k of them are faulty, so or say m of them are faulty. So, each of these faulty site, it can say each of these n faulty site, it can have one of these k faults, or the site may be fault free. As a result, the line can be at a possible in any of these possible k plus 1 states. So, if you consider simultaneous, if you consider multiple fault occurring simultaneously, then the total number of multiple faults is given by this expression k plus 1 to the power n minus 1, where this 1 is the good circuit. So, the fault free circuit. So, that is excluded. So, this is the number of multiple faults that can occur. Naturally, this is impractical. So, if we have got for accepting very small circuits, where this n, the number of lines in the circuit is very small, so this becomes impractical. So, normally what is done, this single fault model is used, that is circuit has got only one fault, and it is said that though there are n potential faulty sites, it is assumed that only one of those sites may become faulty at any point of time. So, that way so each of these n locations, they may have a fault or may not have a fault. So, as a result, only one of them may become faulty. So, I have got this k into n number of single faults that are possible in the system, because this out of this n, only one point will be faulty, and that one point may pick up any of these k faults. So, total number of possibilities is k into n. So, this type of fault model, single fault model, though it is very simplistic, but this helps in generating developing algorithms for doing this testing efficiently, and it has been observed that good single fault coverage it generally implies good multiple fault coverage. So, this is some experimental result that shows that if you do not use a multiple fault or multiple fault model where a circuit can have multiple faults. So, if we do not use that model, even in that case, so we can have this if you use the single fault model, and we have got the test pattern set generated using the single fault model. So, for multiple fault model also, that for multiple faults also, that particular test set can be applied, and if we apply that test set, so it gives reasonably good level of detection of multiple faults as well. So, that is why in most of our discussion, so we will never be talking about this multiple fault model or multiple faults occurring in a circuit simultaneously. So, we will most of the time we will be talking about single fault model, that is, we will assume that the entire circuit has got a single fault. Now, there are some faults which are equivalent, that is, one or more single fault that have identical behavior for all possible input patterns. So, some cases it is not possible to detect such faults because they are becoming equivalent. Like say if I have got an AND gate, now you see that suppose this line I want to check whether this is stuck at 0 or not. So, what will happen? I will apply to check whether this line is stuck at 1. So, I will apply a pattern 1 1 and I will see the output. If at the output I get a 1, I know that this line is not stuck at 0. So, but if I get a 0, so assuming that these two lines are correct, because under that single fault model only one line can be faulty. So, knowing that these two lines are correct, so I will conclude that this line has got a stuck at 0 fault. By applying the pattern 1 1, I get it. Now, consider the situation that this line is okay, but this line is I want to check whether this line is stuck at 0 or not. In this case also I have to apply the pattern 1 1 and see what is the response. So, if I get a 1, I will say that no, the line is not stuck at 0, but if I get a 0, then I will say that okay, this line is stuck at 0. Now, for both the faults, like this line stuck at 0 and this line stuck at 0, the response of the AND gate is same for all the test cases. So, as a result, so I cannot distinguish between these two faults. The same is true for the other input as well. So, one or more single faults that have identical behavior for all possible input patterns, so they become equivalent faults. So, we cannot have a test generation process that can distinguish between these two occurrence of these two faults. So, from this entire set I need to consider only one fault, knowing that all others are equivalent. Okay. So, they need not be tried out. So, that any test pattern set that can detect this fault will also detect the other faults in that equivalent set. So, I do not need to have separate test generation process for each fault in this equivalent class. So, that is one thing. So, this is the definition of equivalent fault. So, now knowing that there are equivalent faults, so we can do fault collapsing. Fault collapsing means we want to reduce the number of faults that we need to consider for the test generation process. We remove these equivalent faults except for one to be simulated. So, we keep only a single fault from the entire equivalency class, and remaining all we collapse into that particular fault. So, this will reduce the total number of faults. As a result, this will reduce the fault simulation time, this will also reduce the test generation time. So, this is the first step that is done under a particular fault model. So, we will find out the equivalent faults for a circuit. For each of the equivalent class, we will take only one fault, and that they will do fault collapsing, and then the set of faults that we get finally, they are all non-equivalent faults, and for those non-equivalent faults, so we have to run our test generation process and our fault simulation process. So, we will continue with this in the next class.